This is David Buckley at Black Rock Castle Observatory, and today we're going to try to demonstrate an activity whose purpose is to demonstrate to students why exoplanet systems seem to be so much smaller than you would think. What we're going to be doing is simulating exoplanet transits across a styrofoam star. Okay, this star is a styrofoam ball about the size of a grapefruit, and the exoplanets will be these little styrofoam balls about the size of a very large blueberry. You can get these in pretty much any craft store. You also need some wooden barbecue skewers, which you can find in most grocery stores. If you can't find these, or you don't have easy access to these, a very stiff set of wires will do, but those might bend a little too much and rotate a little bit too much, so that's these are preferable, I think. Also a black marker, and you might also want a pencil, one with the six-sided flat sides. At any rate, the first thing, oh, and also a tube from the inside of a paper towel. All right, that's going to be your telescope at the end. The first thing to do, and this is actually harder than you would think, if you have a styrofoam ball that has a seam around the middle, you can use that as the star's equator. The tricky part is to punch one of the barbecue skewers through the styrofoam ball so that it goes directly through the center as though this were the axis of rotation. But it doesn't really have to be perfect. Okay, my equator is wobbling a little bit. Now if you have a styrofoam ball that doesn't have a seam to it, then basically just punch your axis through the center, and then you can sort of draw an equator by rotating the ball. Okay, now we need planets. Ultimately we're going to make planets that look like this. You have one that's on a shortened skewer and one that's on a long skewer. You want to color them so that the dark side of the planet is pointing away from the star. We're going to be sticking the barbecue skewers into our styrofoam star, so the light side will be facing the star and the dark side will be facing away. All right. So the way you do that, these are very conveniently, these little styrofoam balls conveniently have little holes in them that almost perfectly fit on the end of the barbecue skewer. Okay, so once you put one on like that, this can be the planet that will be farthest away from our star. Well, all you have to do is put your black marker right at the middle of that and rotate, and that will give you a nice equator, or rather a terminator of the planet. The terminator is the line between light and darkness. Okay, so once you've got that, then you can fill in the dark side of the planet. All right, so now we have our dark side. You can come to the dark side now, and you poke your skewer right into the equator of the star. Okay, and then you do the whole process over again, but this time with a skewer that's cut or snapped to about a little bit less than half, maybe about a third the size of the full skewer. Okay, and so you take that inner planet and you also poke it. What you want to do is rotate and see where the plane of rotation is, and then put this maybe a 20 to 30 degree angle away from our more distant planet. And so what you should have is an axis of rotation that's straight up and down, and the planets should be sticking out horizontally from the star. Now, one thing I'd like to point out is this is not the way planets really orbit the star. What you will have is you will have the inner planet going around much faster than the outer planet. Okay. But what we're trying to demonstrate here is how the tilt of the planes of the orbits have something to do with the selection effect of how you discover inner planets versus outer planets. Okay, so we're going to have our planets go around our star as the star turns. Again, that is not an astronomically correct thing, but it works very nicely just for this demonstration. So our inner planet is going to be rotating at the same rate as the outer planet. Again, that's not accurate, but it does show the difference between the transits. Okay, and again, the transit is when the planet crosses the disk of the star. Now, for an exoplanet, these stars would be so far away that you wouldn't actually see the transit, but you would be able to detect a very, very, very slight dimming of the star when compared with other stars that are not changing in brightness. And that's how we detect these exoplanets. Okay. But what we're going to do is we're going to take this model and we're going to put it on the other side of the classroom and have a student look through our very inexpensive artificial telescope, which in this case is a paper towel holder. Okay. So when you look at the star from a distance, the student will be able to see when the transits occur and when they don't. And the key to this demonstration is, if the student is watching from directly over in that direction, at first you want to keep the stars edge on, the rotation edge on to the line of sight of the student, like this. But then you want to ever so slightly tilt it either toward or away from the student, so that now the orbits are tilted slightly this way. And the student will see whether the inner planet or the outer planet transits or not. What we expect to happen, and what will happen if this is done correctly, is that the inner planet will continue to transit a lot longer than the outer planet, regardless of tilt, because it's so much closer. So even when the orbits are tilted a reasonable angle, the inner planet will still obscure some of the star, and the outer planet will miss the star. Okay? And the idea for the student is to hopefully figure out that this might be the reason why exoplanet systems seem to have so many planets near the star and very, very few planets far away. It's just a matter that they're easier to detect. There are more sophisticated demonstrations that we have links to in the exercise, and you can check those for finding out how the star dims with the transits.